All right, now we're using the concentration unit called mole fraction. Now, mole fraction is useful, especially when we're talking about gas laws, is when we would use this particular unit, mole fraction. You may remember in Chem 1 when we did gas laws that this was something that we used. For example, when we looked at Dalton's law. All right, so mole fraction is going to be equal to this. The mole fraction of whichever component that you are interested in is the moles of that particular component divided by the sum of the moles of all the components. You may notice that this looks very familiar to percent by mass. The mass of the component divided by the total mass. And it is very similar the concept. So we have moles of our component divided by the total number of moles of all of the components in the solution. So here they're asking us to calculate the mole fraction of heptane in this solution. So let's see what we have. We have a solution that is made by mixing 62 grams of heptane and 69 grams of chloroform. Okay, so what we need to do is take those masses, 62 grams of heptane, and we need to take the 69 grams of chloroform and convert it to moles. Now we could do that because we have the chemical formula here, and with some simple math, or if it's given to you in ALEKS, or you can Google these molar masses, we can very quickly convert from grams to number of moles. The molar mass of heptane is 100.21 grams in 1 mole, and the molar mass of chloroform is 119.38 grams per mole. So if I do the math here, 62 divided by 100.21 gives me 0.6187 moles, and I'm trying not to round these intermediate values. You don't want to round them to 2 significant digits right off the bat. Go ahead and carry out a little bit. I usually carry out to 4 or 5 decimal places. And then if I take 69 and divide by 119.38, I get 0.57799 moles. Okay? So in this solution, I have this many moles of heptane and this many moles of chloroform. So they want the mole fraction of heptane. So if that is the component we are interested in, then I take this value and I place it in the numerator because it is the moles of the component that we are interested in. I'm going to divide that by the sum of the moles of all components. So I'm going to have to add the number of moles of heptane to the number of moles of chloroform. And what I get when I take this number and divide it by these two numbers added together, so you have to make sure if you try to put this into your calculator, you need to place this within parentheses to separate this function from the division. So if you want to put it all in at once, you need to put in your calculator this number divided by open parentheses, this plus this, close parentheses. And so what we get is 0.517. We're going to round that to 2 significant digits, 0.52. Now, we're not going to multiply this by 100 like we did for percent by mass, because again, that is a percentage. Multiplying it by 100, since percent is out of 100, will convert the decimal to a percentage. Here, I'm going to leave it at 0.52. And that makes sense because this is a mole fraction. A fraction is, when I think of a fraction, what's 1 over 2 or 1/2, for example, is a decimal, 0.5. What is 3/4 as a decimal? 0.75. So as long as the numerator is less than the denominator, it's some number less than 1. Now, if the numerator and the denominator are the same, then it's 1. So when I look here, because this value is always going to be less than the total sum, or it could be fairly close to equal to. But as long as there's more than one component, it's always going to be, this is always going to be less than the sum of these components as far as the number of moles. And so the mole fraction of this component should always be less than 1. It could be very close, but if there are two components, it should always be less than 1. And that's what we see here. It's actually much less than 1. Okay? So out of all of the moles in this solution, a little more than half of the total number of moles is attributed to the moles of heptane. All right?